Welcome everyone. In this video lecture, we will solve a GATE 2014 question in which we have to find the drain current. So basically, in this question, the figure shown here, a diode connected MOS device. When the gate and drain is sorted, it is called as the diode connected device. Okay. So for this question, for the N channel MOS transistor shown here, and it have a threshold voltage 0.8 volt, and we have to neglect the channel length modulation. And in the question it is given when the drain voltage is zero point 0.6 volt, the drain current id is zero point 0.5 milliampere, and if we adjust the voltage of vd by changing r and vdd to 2 voltage, we have to find the value of id. So in the question, the given things are threshold voltage VTH. I am writing 0.8 volt. Okay, this one is given, and channel length modulation neglected, so no need to write. And VD value is given 1.6 volt. At that time, the corresponding ID current is observed as zero point 0.5 milliampere. Okay. Now when the VD value is adjusted to 2 volt, okay, so we have to find the value of the new id for this one. Okay, say we can say this one is id days. Okay, so we have to first decide in which mode the transistor operating, either saturation or linear. Okay, so as we know, the id vds characteristics, I am just drawing the this vertical axis, that is our y axis in id, or then this vds is in volt. So if we plot the characteristic curve, it have somehow this type of structure. Okay, so we have to know this one, and this value will be vgs minus vt, and this region is the saturation one, saturation region. Okay, channel length modulation, so lambda 0, and this one, this region is the linear one. Okay, this one linear. Okay, this up to this region. So so we have to find the drain current. So as we know, for the saturation, I am just writing here, for saturation region. Okay, the saturation region, the vds value will be greater than equals to vgs minus vt. This one is the condition. And for linear region, this vds value will be less than equals to vgs minus vt. Okay, so we have to decide first. For saturation region, once again I am saying vds is greater than vgs minus vt. For linear, vds is less than vgs minus vt. Okay, so in such type of case, in case of diode connected device, so in this case, this gate voltage and drain voltage, that is our vg, equals to vd, having the same potential. Okay, and vs is connected to ground, so we are writing 0. So first, for the first case, we are saying, for suppose for vds is, I am just checking it is linear situation. So first I am taking this situation. So we can say the source is grounded, so one can write in more detail vgs minus vs minus vt. So this vs will be cancelled, both are 0, also we have to. And vt is greater than vg minus vt, all are the condition for the saturation region. And this vd, we can write it vd minus vt. Okay, because vd equals to vg from figure. Okay, so what we observed, the this value, that is our, we can finally observe that If this one is VD is somehow 5, so the 5 minus is it's suppose 0.8 volt. So this value will be always greater. So this one is the correct case. So no need to go for the saturation linear assumption. So this one the transistor is in the saturation mode. So if this type of thing is there, diode connected device. So I am writing here for the theory purpose. For diode connected device, diode connected MOS device, transistor is operating in the transistor will operate in the saturation mode. Okay, so this one is some theory. Numerical is very easy. So first we have to know some theory. So just this one is our saturation. The device is in the saturation. So now there are two conditions are given. Okay, so for this purpose, what we are doing, we are writing the drain current equation. So we can write ID equals to mu n cox w by L VGS minus VT whole square. This one is L. Okay. VGS minus VT whole square for the saturation region. I am not writing for the linear region equation. So saturation region equation. So in the very first case, it is given this condition is given VD and VD is same as that of VG. So we can write in this case VD, okay, pencil VD equals to VG. So we can simply VG S will be 0. So this term what we observe in this case this term is our unknown term. So if we find this term and for the other one VD is also given, so we can easily find the value of IDS for the same type of transistor. Okay, because everything is given VTH, or we can write it this one as a VTH. Okay, so from here what we can write ID value is, because for this case VD is given, VD equals to VG, we can directly write as 1.6 volt. Okay, for this one ID is given 0.5 milliampere, I am also writing, and VTH is 0.8 volt. So from this one, from this known parameter, from this known parameter, okay, we can find the value of mu n cux wl as a unknown. So once again I am writing, or I am just simplifying this drain current equation. IDH Kn VGS minus VTH whole square, where this Kn is mu n cox w by L. Okay, so we have to find the value of Kn first. Okay, so ID value is how much? ID value is given 0.5 milliampere, so I am just writing 0.5 milli. Okay, Kn and VGS value. So VGS, that is simply our 1.6, because get to source VG minus VS, or VG is same as that of VD. Okay, VG equals to VD. So and VD is nothing but simply our 1.6 and VS is 0, so it should be 1.6. I'm directly writing 1.6 minus VTH 0.8 whole square. So from this one we can easily find Kn as a 0.5 milliampere by, we can write it 1.6 minus 0.8, so it should be 0.8 into 0.8 volt square. Okay, better to write this units also. So if we solve, this point will be cancelled out, this point will be, so one can write 5 by 8 into 0.8, so just cancel this 10, so milliampere by volt square. So 50 by 64. Okay, we can write milliampere by volt square. Okay, so this kn value, the final value of this kn, I am writing 50 by 64 milliampere by volt square. I am highlighting this. Okay, so now this one is one condition. When one condition is given, now in the question we have to find id value is still in saturation. For vd value 2 volt, for vd value 2 volt. Now we have to find vd, for vd 2 volt, the drain current. Okay, I am writing this one as id dash. So now kn is now known to us, that is about 50 by 64 milliampere by volt square. So now again this one, the transistor will operate in the saturation. So we can write as simply, for the same type of MOS transistor, we are taking the transconductance as same. So again this should be VGS minus VT whole square. Simple. Okay, now 50 by 64, I am writing milli. Okay, ampere volt square no need to write. Okay, or ampere, or if you want to write you can write. Okay, into VGS. Okay, so VG is here also. VG is same as that of VD, and VGS equals to VG minus VS. VS is 0, so we can write VD minus VS, so it is same as that of VD. So we can write it VD, so VD value, or once again I am writing it like that. Okay, so 50 by 64, if we want to write milliampere by volt square. Okay, so milliampere and VD value is 2 volt, it is adjusted to 2 volt minus VT. VT will be also same, VT value is also same, 0.8. So we can write it VTH 2 minus 0.8 whole square, and this should be unit will be volt square. So this volt square cancel out, so it should be in milliampere range. So it should be 50 by 64 into 1.2 whole square. Okay, or just try to solve this one. Only now we have to solve this one. And this should be 100, and this should be in milliampere. Okay, so this should be cancel out 5, 2. Okay, 2, then it should be 6. Okay, so it should be, if we directly use the calculator, it should be 12 into 6, 72 by 64. So I am just using my calculator. So 72 by 64, so it should be 1.125. Okay, in milliampere, milliampere, so it should be 1.125 milliampere. So the correct value of id will be 1.125 milliampere. So this one will be the id value, new id. Okay, just we have to apply this one, the unknown thing, watch kn that we have find. Okay, so the correct answer for this question will be this. Okay, 1.125 milliampere. Okay, they are asking in milliampere, so we have to direct write 1.125 milliampere. So this is all about this simple question. So thank you for watching.